Guys, so following from our video about dot product, this is going to be a video going over some of the intuitions behind the cross product to give you guys a better understanding of where the cross product comes from and a better way to visualize it. Okay, so we've talked about the dot product already and how a dot product gives us a similarity score or a parallelness score between two vectors. The other thing to keep in mind about the dot product is that its input is two vectors and its output is a scalar. Okay, so dot product is one way to multiply two vectors, okay? But let's try to think about a different metric which can give us some more information about two vectors. Instead of giving us a score of how similar they are, what about a score of how different they are? What about a differentness score? Or instead of similarity, we can say an independence score. How independent are two vectors from each other? Okay. Well, what are the criteria for a metric like this? First of all, we want for when two vectors are parallel. When vectors are parallel, we want our metric to be low. But when vectors are orthogonal, independent, when they're the most different from each other, and when they have the least in common and the least similar between each other, when vectors are normal to each other, orthogonal, we want this metric to be high. Okay. Well, how do we do this? I want you to think a little bit about how you can find a score like this, and then I'm going to show you guys an animation which will hopefully clear things. Alright guys, so in this animation I have two vectors, okay? These vectors define a parallelogram. This number is the area of the parallelogram, and you can see as the vectors become parallel, the area went to 0. Now as we're increasing the angle between the vectors again, we're increasing and increasing it, the area is going up, it's going up, it's going up. When do you guys think it will hit a maximum? So it's still increasing, still increasing, still increasing. Notice how the angle between the two vectors is now 90 degrees, and now it starts to go back down again. So it hit a maximum when the angle between the two vectors was 90 degrees. So this is great. The area of the parallelogram defined by the vectors gives us the metric that we want. Alright, so we can now we've now confirmed visually that we can use the area defined by a parallelogram of two vectors to be our metric. Okay, great. We have the parallelogram. How do we find the area of the parallelogram? Well, area, keep in mind, area is equal to base times height, right? So we pick one side as to be the base, and for example, let's pick in this case B to be the base, and then this is going to be the height. The easiest way to see this formula is true is to notice that basically this right triangle here, if I cut and paste it to this side, then it's going to be a rectangle, and then it's just base times height, just normal area of a rectangle, okay? So how do we find this height? That's what we need to do in order to find the area of the parallelogram and figure out our metric. We can just use simple trigonometry, okay? We have this angle between the two vectors here, and what is h? Well, h equals to magnitude of a, right, times the opposite over the hypotenuse, because opposite is h, opposite to theta is h, the hypotenuse is a. So then we have that the h should be equal to a times sine theta. So that's h. B base, we've already confirmed that this is going to be equal to the magnitude of the vector b. So an area is equal to a times b times sine theta. Okay, great. What does this look like? This should be familiar to you as the magnitude of the cross product. Magnitude of the cross product is equal to the area of this parallelogram, right? And this is an easy way to see how we derive it and where the sine theta comes in. Sine theta is also important because sine theta, unlike cos theta, remember we discussed in the dot product video why cos theta is important? Sine theta is at a maximum when theta is 90 degrees, and it's 0 when theta is 0 degrees. So that's why we see sine theta here. And it meshes well with the two criteria we gave for our metric. Okay, so this is great, but this is only part of the story, right? Because we know the cross product doesn't just give you a scalar like the dot product. The cross product gives you a vector. And this really big formula is the formula for the cross product, okay? It's not just a magnitude, there's also direction, there's also a vector. And the vector it gives us is orthogonal to the two vectors we put in. So how do we get to this formula? Well, the trick is we need to find the area of this parallelogram, right? Let's try to find it, though, without invoking sine theta. Let's try to find it a different way, a more visual way, and see if that gets us closer to figuring out this formula. Okay. I want you guys to think about a more visual way of calculating this formula without invoking any trigonometry, okay? How would you calculate the area of this parallelogram without trigonometry? Well, here's one way to do it, okay? Basically, just visually speaking, we have our parallelogram in yellow and this blue part here. We take this whole big shape, subtract it by this blue shape, and we get our original parallelogram. Now, how do we find the areas here? Well, what I've done here is that I've highlighted. I'm going to highlight here. I found the coordinates of each of these points, so that basically we can find the side lengths of the shapes here. Okay, because basically this shape is a rectangle and two triangles, and whoops, same here. This is also a rectangle and two triangles. Okay. So having these coordinates of each point of each of the points will help us a lot. Now, okay, let's figure out the area here. What's this? This length is going to be AX. This length is going to be AY. So we have our first triangle, half AX, AY. And then what's our second triangle here? This is BX, and this is BY, right? So plus half BX, BY. And then this rectangle here, well, we figured out this length is AY, this length is BX. So plus AY times BX. Now, we go here, we have this rectangle and these two triangles. Let's do the same thing all over again. Figure out what's the area of this triangle. Well, we know this length is BX. We know from the point that this is going to be BX. It's going to be BY. And similarly, we just go plus AX and plus AY up here. So this is AX, and this is AY. So here are two triangles, half BX plus half BX BY, which is the area here, plus half AX AY, which is the area here. And then this little rectangle here, the area of it is AX times BY. And you'll notice something nice is that all these terms cancel out. And all we're left with is this. AYBX minus AXBY is equal to the area of this parallelogram. Okay, awesome. This is getting closer to what we had here. Now, what if I said instead of vectors A and B being on the xy plane, vectors A and B were in the, this is when they're in the xy plane, right? What if I said instead, hey, what if they're in the xz plane? So instead of the coordinates being ax, ay, it's going to be ax, az, right? And bx, bz, okay? That's all I'm doing is I'm just swapping out one plane for another. This derivation we did above should still hold. So what happens is in this case, we get, or the zx plane, to be specific, we get ax, bz minus azbx. And if we did it in the yz plane, then we get azby minus aybz. Okay, so these areas should all be basically equal to each other, right? But how do we distinguish between these areas? Well, the distinction is that they're on different planes. We can identify the different planes by the normal to their planes. So basically, if I multiply this by z hat, the normal to the xy plane, multiply this by y hat, and multiply this by x hat, well, line this all up in a matrix and we get exactly our formula for the cross product, okay? So that's cool, but but this is sort of an artificial example, right? If we have an actual, a vector A and a vector B, how do you see where the cross product comes from using this derivation that we just did? Well, okay, for starters, there are vectors A and B. If we're taking the cross product of them, can they be in R2? Can we have vector A like this and vector B like this and find another two-dimensional vector that's orthogonal to both of them? That's impossible. So our vectors have to be in R3. We have to have 3 vectors. Okay. So we know that basically what we found up here should give us a vector that's orthogonal to both of our input vectors, right? But there's a few different ways to do that. Actually, there's 2 different ways to do that, right? So basically, we can have a perpendicular vector like this or a perpendicular vector like this, right? So how do we decide which one we're going to pick? Which perpendicular vector becomes the result of the cross product? Well, that's where the right-hand rule comes in, right? The right-hand rule tells us that, okay, if you're doing A cross B, then what you're going to do is you're going to put your index finger where A is, and your middle finger where B is, and then you're going to pick this vector to be your orthogonal vector, okay? Your cross product result. And if instead you're doing B cross A, then you're going to pick this other vector, right? So then what happens is A cross B equal to negative B cross A. And there's actually a reason for this right-hand rule convention, which we'll get to in a little bit. There's a very good practical reason for it. Okay, but anyways, how does this whole parallelogram area stuff fit in when we have a 2 3D vectors? Well, I'm going to show you an animation to clear. So here we can see we're defining 2 3D vectors and the parallelogram between them. And now what I'm going to do is I'm just going to project this parallelogram onto the different axes, okay? And these are the different, AX, BY, AY, BZ areas that we just discussed earlier. Each component of the cross product is the area of these different parallelograms. And we decide the sign of the area of this, because this is a signed area, we decide what sign the area is going to have based on the right-hand rule, which we discussed earlier. So hopefully now you should have a little bit of a better idea of where the cross product comes from, how we come up with the formula for it, and what it means. But why do we need it? Why do we use it? Well, if you've ever opened the bottle cap, then you've made use of the right-hand rule. And so here's a GIF that explains where the right-hand rule sort of comes from. You can see this is a wrench, and you're spinning a torque with the wrench, right? Basically, the direction that the screw comes up or down depends on the right-hand rule, okay? So this screw, if you're pushing clockwise, the screw goes down. If you're pushing counterclockwise, then the screw goes up, and that's based on the right-hand rule, which you can see from this little animation here. So hopefully this has cleared up some of your questions about cross product. If you have any more questions, feel free to go ahead and contact me and talk to me in tutorial.